Good morning, everyone. I am delighted to welcome you all today. Today, we will be exploring the complete syllabus for Class 12 Physics for the academic year 2026-27. This presentation is brought to you by Ansar Sir. We'll go over the entire syllabus in detail, giving you a clear roadmap of what to expect this year. So, let's get started and make this a productive session. Let's take a closer look at the mark distribution across the different sections. On the left side, we have Section A, which covers a total of 35 marks. This section includes topics like electrostatics, which is worth 8 marks, and current electricity for 7 marks. It also dives into magnetic effects of current and magnetism, again 8 marks, and electromagnetic induction and alternating current, which also carry 8 marks. Additionally, electromagnetic waves is a smaller section with 4 marks. Moving to the right side, we see Section B, also totaling 35 marks. This section emphasizes optics, which is a significant part with 13 marks. It also covers the dual nature of matter and radiation for 6 marks, atoms and nuclei for 8 marks, and electronic devices for 8 marks. Overall, the marks division shows us how the syllabus is balanced between these core areas. The sections are designed to test a wide range of concepts, from fundamental electrostatics to modern physics topics like atomic structure and electronic devices. Understanding this breakdown helps us prioritize our study focus and ensures we're prepared for questions across all these important topics. Let's delve into some fundamental concepts of electrostatics. First, we have electric charges and their conservation, meaning charges are neither created nor destroyed. Coulomb's law tells us how 2 charges exert forces on each other, which is proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. This law extends to multiple charges, allowing us to analyze complex systems by summing individual interactions through the superposition principle. Next, consider continuous charge distributions, where charge is spread over a volume, surface, or line, rather than concentrated at a point. This leads us to the electric field, which is the region around a charge where it influences other charges. The electric field due to a point charge is straightforward. It's directed radially and diminishes with distance. Field lines help us visualize this, showing the direction and strength of the field. We also study electric dipoles, pairs of equal and opposite charges separated by a small distance. The field of a dipole has unique characteristics, and when placed in a uniform electric field, it experiences a torque, tending to align the dipole with the field. Moving on, electric flux measures the number of electric field lines passing through a surface. Gauss's law states that the total electric flux through a closed surface is proportional to the enclosed charge. This principle simplifies calculations for symmetric charge distributions, like line charges, plane sheets, or spherical shells. Now let's talk about electric potential, the work done per unit charge in bringing a charge from infinity to a point in an electric field. The potential due to a point charge or dipole can be calculated, and we often use equipotential surfaces where the potential is constant to visualize this. Electrostatic potential energy is the energy stored in a system of charges. Conductors and insulators differ in how charges behave. Conductors allow free movement of charges, while insulators do not. Materials called dielectrics can be polarized. This affects the electric field and potential within them. Finally, we have capacitors, devices that store electric energy. The capacitance measures how much charge a capacitor can hold at a given potential difference. When capacitors are combined in series or parallel, the total capacitance changes accordingly. The energy stored in a capacitor is proportional to the square of the voltage and the capacitance. All these concepts form the core of electrostatics and help us understand how electric charges interact and store energy. Let's dive into Section A, which carries a total of 35 marks. Here, we explore the fundamental concepts of electric current, which is essentially the flow of charges through conductors. Think of it as how electrons move through a wire. The drift velocity describes how fast these charges are moving, and mobility tells us how easily they can move in a material. Next, we look at Ohm's law, a cornerstone in understanding electrical circuits. It states that the current flowing through a conductor is directly proportional to the voltage across it, provided temperature stays constant. This relationship is often illustrated through VI characteristics, which can be linear for some materials, but nonlinear for others, indicating different behaviors. We also consider electrical energy and power, how energy is transferred and converted in circuits. Understanding resistivity and conductivity helps us see why materials behave differently when conducting electricity. The resistance of a material usually depends on temperature. Typically, resistance increases as temperature rises. Moving on, we examine the internal resistance of a cell, which is the resistance within the cell itself, affecting how much voltage it can supply. EMF, or electromotive force, is the maximum potential difference a cell can provide, while potential difference is what's actually across the terminals during operation. We then explore how multiple cells can be combined in series or parallel, impacting the overall voltage and current. To analyze complex circuits, we use Kirchhoff's laws, Kirchhoff's current law, which states that the total current entering a junction equals the total leaving, and Kirchhoff's voltage law, which says the sum of potential differences around a loop is zero. These laws are crucial in circuit analysis. Finally, we look at the Wheatstone bridge, a precise method for measuring unknown resistances by balancing two legs of a circuit. All these concepts are interconnected and form the backbone of understanding current electricity, which is essential in both practical applications and theoretical physics. Let's begin by exploring the concept of a magnetic field, which is fundamental to understanding electromagnetism. The magnetic field around a current-carrying conductor was demonstrated through Ørsted's experiment, which showed that an electric current produces a magnetic field. Moving forward, the Biot-Savart law helps us calculate the magnetic field generated by a small segment of current, and it's widely applicable in various situations. Ampere's law, on the other hand, simplifies these calculations for more symmetrical configurations, linking magnetic fields to the currents that produce them. Next, we look at the force experienced by a moving charge or a current-carrying conductor within a magnetic field. This force is the basis for many electromagnetic devices. When two parallel conductors carry currents, they exert forces on each other, either attractive or repulsive, depending on the direction of the currents. We also examine the torque on a current loop, which is crucial for understanding how electric motors work. A moving coil galvanometer uses this principle, and by modifying it, we can convert it into an ammeter or voltmeter, enabling us to measure current and voltage accurately. Furthermore, the concept of a magnetic dipole explains how objects like bar magnets produce magnetic fields. These fields are visualized through magnetic field lines, which help us understand the magnetic influence in space. Substances respond differently to magnetic fields. Diamagnetic materials are repelled, paramagnetic materials are weakly attracted, and ferromagnetic materials are strongly attracted and can retain magnetization. All these concepts tie together to give us a comprehensive understanding of the magnetic effects of current and magnetism, which is essential for many technological applications and advances in electromagnetism. Let's dive into Section A, which carries a total of 35 marks. Here, we'll explore Faraday's laws of electromagnetic induction, which are fundamental to understanding how electric currents are generated in conductors exposed to changing magnetic fields. We'll look at induced EMF, or electromotive force, and how it causes current to flow. Next, we'll discuss Lenz's law, which tells us the direction of the induced current, always opposing the change that caused it. This naturally connects to the concepts of self-induction, where a coil opposes changes in its own current, and mutual induction, where one coil induces a current in another nearby coil. Moving into alternating current, or AC, we'll examine how the peak and RMS values relate to the voltage and current we see in AC circuits. Understanding reactance and impedance is crucial here, reactance being the opposition caused by inductors and capacitors, and impedance being the total opposition in the circuit. We'll then explore LCR circuits, which combine inductors, capacitors, and resistors. These circuits can resonate at a specific frequency, leading to maximum current flow, an important phenomenon in tuning circuits. Power in AC circuits is another key point. We need to understand how power is calculated and the significance of the power factor, which indicates how effectively the circuit uses electrical power. Finally, we'll look at practical devices like AC generators, which produce alternating current, and transformers, which transfer electrical energy efficiently over distances through electromagnetic induction. All these concepts tie back to the overarching theme of electromagnetic induction and how it underpins much of our modern electrical technology. Let's explore Section A, which is worth a total of 35 marks. Here, we'll delve into the need for displacement current, the concept of electromagnetic waves, and their key properties. Understanding why displacement current was introduced is crucial because it helped Maxwell complete his equations, allowing us to explain how changing electric fields produce magnetic fields and vice versa. This leads us directly into the concept of electromagnetic waves, oscillating electric and magnetic fields that can travel through space. Next, we'll look at the electromagnetic spectrum, which is essentially the range of all possible electromagnetic waves. It includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each type has unique properties and specific uses, from communication and cooking to medical imaging and cancer treatment. Recognizing these different waves and their applications emphasizes how integral electromagnetic waves are to our daily lives. This section ties into the overall theme of understanding how electromagnetic phenomena underpin many modern technologies. By grasping these concepts, we gain insight into the fundamental nature of light and other radiation, which is essential for many scientific and practical advancements. Now let's dive into Section B, which is worth a total of 35 marks. Here, we'll explore the reflection of light using spherical mirrors and understand the mirror formula, which helps us relate object distance, image distance, and focal length. We'll also look at refraction and the fascinating phenomenon of total internal reflection, along with some practical applications. Moving on, we'll discuss lenses, their formulas, how they magnify objects, and how to calculate their power. We'll also see how combining lenses can create more complex optical systems. Next, we'll examine important optical instruments like the microscope and telescope, which have revolutionized our way of seeing tiny details and distant worlds. Switching gears in wave optics, we explore how light behaves as a wave. We'll cover interference, including Young's double-slit experiment, which beautifully demonstrates how waves combine constructively and destructively. Then, diffraction, which explains how light bends around obstacles, and polarization, where light waves are filtered to oscillate in specific directions. All these concepts come together to deepen our understanding of optics, connecting basic principles to advanced applications in science and technology. Now let's move on to Section B, which is worth a total of 35 marks. In this section, we'll explore the dual nature of radiation and the photoelectric effect. This is a fascinating area because it reveals how light can behave both as a wave and as a particle. We'll look at Einstein's photoelectric equation, which explains how electrons are emitted from a metal's surface when light shines on it. This was groundbreaking because it demonstrated the particle-like behavior of light, which was a major shift from the classical wave theory. Next, we'll discuss the wave nature of matter, which might sound surprising because we usually associate waves with light or sound. But in quantum physics, particles like electrons also exhibit wave-like properties. This concept is captured beautifully in de Broglie's relation, which connects a particle's momentum to its wavelength. Together, these ideas form the core of the dual nature of matter and radiation, highlighting how quantum mechanics challenges our traditional understanding of physics. This section ties into the overall theme of understanding the fundamental nature of particles and waves at the microscopic level. Now let's move on to Section B, which carries a total of 35 marks. We'll start with the Rutherford model, which was one of the earliest attempts to understand atomic structure. Rutherford proposed that the atom has a small, dense nucleus at its center, with electrons orbiting around it, much like planets around the sun. Building on that, the Bohr model introduced the idea of quantized energy levels, meaning electrons occupy specific orbits with defined energies and can jump between them by absorbing or emitting energy. This leads us to the concept of energy levels, which are fundamental to understanding atomic spectra. Next, we have the hydrogen spectrum, which is a classic example of how atoms emit specific wavelengths of light. Although we often look at it qualitatively, it beautifully illustrates the idea of discrete energy transitions within the atom. Moving forward, we delve into nuclear structure, where we explore isotopes. These are atoms of the same element but with different numbers of neutrons. This variation affects their mass and stability. The mass-energy relation, formulated by Einstein, shows that mass can be converted into energy, which is crucial when we talk about nuclear reactions. Speaking of nuclear reactions, radioactivity involves unstable nuclei emitting particles or radiation to reach stability. This process can lead to nuclear fission, where a heavy nucleus splits into smaller nuclei, releasing a lot of energy, or nuclear fusion, where light nuclei combine to form heavier ones, again releasing energy. The concept of binding energy ties it all together. It's the energy required to hold a nucleus together, and the amount of this energy determines the stability of an isotope. Throughout this section, the key theme is understanding how atomic and nuclear models explain the behavior and properties of atoms and nuclei, which is central to grasping modern physics and its applications. Now, let's delve into Section B, which carries a total of 35 marks. Here, we'll explore the concept of energy bands in solids, including conductors, insulators, and semiconductors. Understanding these energy bands is fundamental because they determine how materials conduct electricity. Conductors have overlapping energy bands allowing free movement of electrons, while insulators have a wide band gap, making electron flow difficult. Semiconductors sit somewhere in between, with a smaller band gap that can be manipulated for various applications. Next, we'll look at the semiconductor diode, a crucial electronic device. Its IV characteristics reveal how it behaves under forward and reverse bias. In forward bias, the diode allows current to flow easily once the threshold voltage is reached. Conversely, in reverse bias, the current is minimal until breakdown occurs. This behavior is key to many electronic functions. Moving on, consider the diode's role as a rectifier. It converts alternating current into direct current, which is essential in power supplies. Diodes also have many basic applications in circuits, such as signal demodulation and voltage regulation. Finally, this section ties into our broader theme of electronic devices, highlighting how understanding these fundamental principles enables us to design and utilize devices that are integral to modern electronics.